Very good, very good. So no travel, right? Or very restricted, very limited?
Yeah, we can go to a field site with approval, but no flying, no driving, typically no more than 50 miles. So.
Oh, there is a restriction on the mileage too.
Yeah, yeah. I think, just so that you don't stay overnight somewhere and more exposure.
Yeah, definitely.
Okay, there's Wei Wei.
Yeah, Huawei is here.
Hello.
Hello, how are you doing, Huawei?
Good, good. How are you doing?
Good, good. It looks like it's cold in Colorado. It's in Fort Collins.
Yes, and it's smoky.
Yeah, I went for a walk this morning and it was snowing, but it wasn't snowing frozen water. It was snowing ash from the fire.
Yes, yes. Rain ash.
Yeah.
Now we're blessed. I mean, today is right now is 81 degree and is going to be 84 today.
Mm-hmm.
Sounds nice.
Nice.
Reminds you of Hawaii, right? Because this weather is very close. It's 71 to 84. I mean, just. Well, I think we can start. I think we have the quorum, as we would like to say. So we have about 25 people so far. So we should be good. So I think for the sake of time, and since we have 2 speakers today, so I think we would better keep going, right? So welcome. Okay, I'm gonna share my screen first and everybody can share his screen. So after I share my screen, you can, I'm gonna make a brief introduction, then you can share your screen.
Okay.
Mm-hmm.
So I'm assuming, okay, so, all right. Good morning, everybody, and welcome to the 2020 Fall College of Agriculture and Human Science Research Seminar Series. This is our 8th week, because last week we didn't have a seminar due to the LDE competition that unfortunately didn't happen. Anyway, this is the program for the semester so far, and today we're going to have, it's October 22nd, we're going to have both Dr. Green and Dr. Zhang, who are going to be talking to us about modern tools for research in precision agriculture and conservation. Keep tuned to next week. We will have we also have 2 speakers that will be talking to us about international agriculture communication and development, and also the use of technology to improve teaching and learning from our colleagues, both Dr. Tobin Redwine and Kim Doley from Texas A&M University. Today's talk, both talks will be part of, as you know, part of the mini series that we have in this seminar series on precision agriculture and opportunities for underserved communities. So a reminder that we had Dr. David Mola, who spoke to us on September 24th, and also Dr. Nagachori, who also followed on October 8th. And today, Dr. Zhang and Dr. Green are going to share with us some of this knowledge about precision agriculture. And so the talk, as I mentioned today, is about modern tools for research in precision agriculture and conservation. We're going to have an overview of the USDA and also the Water Management System Research Unit in Fort Collins. Then Dr. Green is going to talk about field measurement or process modeling. A few question and answer followed after that. And the second part of the seminar will be remote sensing. Dr. Zhang will talk about that one, and followed by question and answers. And I hope we can find some times at the end to talk about opportunities for potential collaboration between our 2 programs. I think with that, I would like to introduce our first speaker, Dr. Tim Green. research hydrologist and lead scientist with ARS, and also faculty affiliated in the Department of Civil Environmental Engineering, Colorado State University. He has a BS in Civil Engineering from the University of Washington, and he has an MS and PhD degree in Civil Environmental Engineering from Stanford University. He also worked as a hydrologist at USGS, Menlo Park, California. He also worked on in the lonely city, as they say, in Perth, with CSRO. Since 1999, he joined ARS, where he's right now. He also spent a sabbatical as a guest professor at the ETH Institute for Terrestrial Ecology in Zurich, Switzerland. For his awards and recognitions and major accomplishments, he's a fellow of the Soil Science Society of America. He is also a member of the UNESCO International Hydrological Program expert panel to conceive a new international project called GRAPHIC. So he's also a member of an industry, he was a member of an industry-led team of scientists, including Monsanto, Bayer, and USGS, based on his work on identifying fractal scaling relationship of pesticides concentration in streams. And this work relates very well with what his father used to do. He's an expert in that area, Dick Green. So derived new stochastic numerical results also. He identified spatial scaling relationship of crop yield, soil, water infiltration, and landscape topography. Dr. Green research is focused on understanding water movement in complex terrain and soils. Also on how to characterize and scale dynamic spatial pattern of terrain and soil, water, and plant variables. His international work includes, as I mentioned, project with UNESCO that funded with UNESCO in Australia. He's also his time in Switzerland, and also he had a funded project by the Brazilian Science Foundation. His ongoing studies address agriculture ecosystem services using the Ag-ES model at the watershed scale. His team works closely with the Object Modeling System, OMS Lab, to develop, test, deploy, and apply Ag-ES watershed model and other tools. With that, I would like to welcome Dr. Tim Green. Welcome, Tim.
Thank you very much, Professor Fares. That was more than expected. You really dug deep into the weeds to find some material, so thank you for that. And hello, everyone. I have one favor to ask you when we come to the end of what I present. If you ask a question, maybe you could turn your video on. That would be nice. Otherwise, I'm speaking to the air. So Dr. Zhang and I decided that I would go first, I guess. So now this is the first part of our modern tools for research in precision agriculture and conservation. So as promised, a little introduction to what ARS is. The Agricultural Research Service is the in-house research agency of the USDA. Many of you will know some of the extension work to universities and funding to universities, but we do the in-house research. We have many national programs, program offices, and an Office of International Research Programs. I'm not sure if all these numbers are up to date, but these will give you a feeling for the number of projects. We're spread across the country with many scientists and, importantly, many long-term support staff who really keep our research going a little longer term than is typically possible. And our mission or motto, in my own words, is feed the world and save the planet. So it's a big view of research affecting what we eat, food security, and environmental security. So our group is called the Water Management and Systems Research Unit. ARS research units in Fort Collins, Colorado were reorganized in 2015 to form a new center. We call it CAR. And our unit was formed by merging the project team from a former unit, Agricultural Systems Research Unit, which was led by Laja Huja, and the Water Management Research Unit led by Tom Trout. And when they retired, we merged, and which is why I get to work with Huiwei now. So we still have 2 projects, and in fact, in our new 5-year plan, we'll be merging the projects as well. But officially, we have management strategies to sustain irrigated agriculture with limited water. And as you know, in the West, we are very interested in what do you do with less water in terms of agriculture. And this project has a research farm with very precise irrigation control, looking at limited water. The other project that I lead is called Spatial Modeling of Agricultural Watersheds, Water and Nutrient Management, and Targeted Conservation Effects, Field to Watershed Scales. So I'll be talking about this model, Agricultural Ecosystem Services, it's called AGES, as well as a lot of the measurements that are integrated with the modeling. Quickly, our team, we have a new research leader, Kyle Douglas Mencken, and he's basically a hydrologist. I won't read all this, but you can see as I show these slides, some of the diversity of what individuals do in their research careers. And then across our unit, we're really trying to blend a diverse set of skills, even personalities, in how we approach our research problems. Our newest scientist, he's been here just over a year, I believe, year and a half, is Dr. Dave Bernard, and he's an agroecologist. And you can see some of the areas that he works in, including fire ecology and restoration. Dr. Louise Comas is a plant physiologist, and excuse me, quick drink. You can see that her work is really focused on the plant under stress, looking at plant stress, growth development, and photosynthetic efficiency. Dr. Kendall DeYoung is an ag engineer, and his specialties are irrigation management, particularly deficit irrigation, detailed views of evapotranspiration. He's out there in the field monitoring something related to ET. And as Dr. Zhang will talk about, he uses infrared thermometry as one indicator of plant stress. And then he's done crop modeling. Dr. Sean Gleason is also a plant physiologist, and he works also in water use efficiency and drought tolerance. And you can see his interest in optimizing water application, but also related to plant genetic traits and the traits of success is one quote there. And then finally, Dr. Huiwei Zhang, and these are her interests, and you'll be hearing from her. And one of her interests is drones. So we have a little drone flying in here, which she'll talk about. So on the lighter side, just a little motivation for my part of the talk. We have a little cartoon. My kids who are grown now, we call this dad joke, but this person says, I thought money didn't grow on trees. Person watering says, it doesn't. This is a bush. So in fact, we are interested in food security, and for the farmer, money is an important part of that. Are you making money off of it? So to give you a little quick agricultural economics lesson, price of wheat right now is about $6 a bushel. We still use bushels in America. 40 bushels per acre could be average to good yield on dryland farming without irrigation. Irrigation can double or more than that, the yield. And from that, we can get dollar amounts of $240 to $480 per acre for growing wheat in one season or 1 year. So how does that relate to you, other than the food you eat? If you think about the iPhone that you would really like to have, it's somewhere around $1,000. And that would take more than 2 acres of irrigated land and more than 4 acres of dry land for you to farm. And that's your gross return, not your net return. So acreage is an important component of that. And we're looking at land conservation and water conservation. By the way, Jordan Bell is with Texas A&M and in your state. So back to this as a motivation and introduction, we're looking at soil and water, other inputs, nutrient management to get food. And food is mammon being money, after Clint Eastwood there. But the thing is, it's really food security. It's giving us security, both economically and in terms of food. What's complicated is we still have to save the planet, in my little motto there. So altogether, it's a global issue of food security and ecosystem sustainability. So to our talk, technology to the rescue, that's kind of the question. And we certainly are in an era where technology is growing leaps and bounds, and we're taking advantage of some of that. So there we go, advance. I'll show you an example from here in Colorado. You can see at the bottom of the screen, the Rocky Mountains. This is actually our field, or this is a different field, but it's near our field. And it's a semi-arid climate. We only get 350 millimeters per year on average. So a little over a foot of precipitation, snow and rain. We have a small watershed in a wheat field, and we're doing all kinds of spatial measurements, including soil water. We've measured infiltration, looked at scaling of infiltration, soil carbon and erosion, plant development, grain yield. And so I'll talk about the measurement of these things as well as the modeling of them. So quickly, let's zoom in from a global scale. This is a North American perspective. All these tools are available to you online, and most of you know how to use them. We can zoom in. This is, they call it HUC 8-digit watersheds. So the whole nation has been separated into smaller watersheds, and our watershed is right there in the middle. It's called the Cache La Poudre. That arrow misses it, but I'll go by. So this is zooming in, and this is the Cache La Poudre watershed with topography going up to the Continental Divide. And within that watershed, our context is a farm where we've been working with a farmer. The other site, which I think Huehue will talk about, is limited irrigation down here in this lower part of the watershed. And this is our town of Fort Collins for reference. So this is zooming into the farm. It's David Drake is the farmer who's allowed us to work in particular on one field. He's given us access to all of his fields, but in particular this wheat field. So we zoom in here, and you can see that it was managed. It's now actually gone into grass, but I'm talking about when it was used for wheat farming, alternating wheat fallow. That means you grow wheat one year and that land sits fallow the next year, actually 14 months in fallow. And it's done in strips to basically help control erosion, predominant wind direction, and you can see water erosion here. So we went out with a GPS on an all-terrain vehicle, survey grade, 5-meter grid cells, and developed a topographic map. So this is the whole field from a high point ridgeline down to the low point. And we can use that type of DEM, digital elevation map, to come up with things like specific catchment area. So for every point in the field, for example, here we have a higher catchment area because a large area drains to it, and other areas may have small contributing area, in fact, flowing in multiple directions. We've delineated this watershed based on where the flume is, and we have multiple soil moisture probes. Each of these have 4 depths, and I'll show you those. So looking down on our field, now we also, in addition to the topography, we have a bunch of instrumentation. This map shows soils that were mapped by NRCS. And again, the flume here are soil moisture probes. We actually have a couple in this corner, which I'll show you. And we put energy balance towers there. And the latest thing we've looked at is cosmic ray sensors to look at soil moisture. And you can see that our soils are all loams, mix of silt, sand, and clay to different degrees. So these are pictures of instrumentation in the field. We have energy balance tower here. We have the cosmic ray sensor here. These are the, it's called Centec, it's a capacitance sensor, which Dr. Fares has worked on. We measure rain. This one in particular is a weighing rain gauge being installed. And this is kind of the gold standard. It has a wind protection to reduce the wind effect. It's actually weighing the amount of water. So next to that, we have a more commonly used tipping bucket sensor, which gives you a tip every, say, 100th of an inch. And from that, we can look at the patterns of rainfall as well as the amount. This is the base of that weighing rain gauge. And then finally, this is an all-terrain vehicle with this is a coring device, but with it we can push sensors into the ground and get hundreds of measurements in a day. So installation of sensors does take some manual labor. This is showing we buried all of the cables back to data loggers. This is the capacitance sensor, which we studied, and its installation. So quickly, as mentioned, I worked with the ETH, or the Swiss Federal University in Zurich, Mike Schwank, and I studied these sensors. And this shows a little cartoon of how you would put a plastic pipe in the ground by drilling an access tube, and actually you would pound that pipe in a little bit in advance and then auger out the soil, and then put these capacitance sensors inside. And from that, they're measuring something that's related to soil moisture, which is strongly related to the dielectric constant of the soil, or the permittivity is another name. So it really is using electrical theory, and we have a capacitance, inductance, L is inductance, resistance circuit, and a resonant frequency of the measurement is related to these quantities, which we can quantify. And again, capacitance will be related to soil moisture. So we wanted to test this, and so we made a little device in the lab, and with that device, we measure the permittivity and the capacitance of this liquid, which we can vary by mixture and at different heats, because it's also temperature sensitive. So quickly go through here. We had made a little scrubber device, the permittivity sensor, and we had a heater. This is actually just a fish tank heater. So this fish tank, we called it, we also used to create a barrier which would allow us to look at the zone of influence of the soil moisture. So this was a study that evolved from what we call the stupid question of what is this sensor measuring? And when we couldn't find anyone who could give us an answer, we did a research study. And this is a simulation of the electrical field. And from that, we were able to determine the zone of influence of this sensor. So that's a capacitance sensor. Now to the time domain reflectometry. This one actually is based on a cable testing method where you measure the travel time of an electrical current through a sensor. And from that, you also estimate the permittivity or dielectric constant. And from that, you get moisture. So this is showing you an average over many dates, over a period of time, the variability of moisture. These are normalized numbers, but within a field, we can have a significant variability. And then finally, those are all essentially point measurements, small volumes. The beauty of the new technology of cosmic ray sensing is you get approximately a hectare area that's measured aerially and a depth of about 30 centimeters or a foot. And we can look at these numbers. We calibrate based on our in-field measurements, and we can get dynamics of soil moisture. This is precipitation on the bottom, and these you can download from a website. And then finally, we have a flume at the edge of the field to collect any runoff that occurs. Again, these are semi-arid fields, very infrequent runoff. What happens when it does run off is a lot of sediment comes down. So we had to replace our initial flume with one that was self-scouring. This is called the Dropbox Weir, and the flume itself works very well. And we do get runoff. I had a bet with a former technician who said he would buy me lunch if it ever ran off before he retired, and it did. And when it runs off, not only water, but soil moves. So this shows the fallow area with wheat stubble in it, a newly planted section, and you see that these soils are much more susceptible to erosion. These are rills, about a foot wide, some of them, and then it converges and flows even through a protected strip. This is Lucretia Sherrod, a soil scientist who looks at soil carbon in our group, and this is just showing some of the extent of that erosion. And then finally, when it hits the flume, in this particular event, it completely overwhelmed these sidewalls that can confine the flow, and we had to replace them. So we do get significant runoff events under wheat fallow. Since conversion to grasses and perennials, we've runoff. So we're studying that as well. But this study will be looking at during the wheat fallow period. And so this is the delineated watershed again. And we're looking at dynamics. Here I'll show you two probes in this corner. So these are versus time for 3 years, starting in 2003. We have precipitation daily amounts to show you those strong events. We had a strong snow event followed by rain in 2003. And the red line is the accumulated precipitation per year. So you can see this year got up to about the average. These were lower. Looking at this probe, this is E2, for example. These are both during the fallow periods. We started very dry, and you can see that near the surface, 30 centimeters is in blue. The soils wetted up significantly, but it took some time for that wetting front to move down. And in fact, we had very little deep water movement, even during this important event. Whereas when the soils start wetter, we get a sharper increase. This one actually saturated near the surface, and it wet up more of the profile. So these data are very important to help us understand dynamics in space and time, and we use them in our modeling. So now moving to the watershed model we call AGES, Agricultural Ecosystem Services. This is a model that has many land areas. We call them hydrological response units that are interconnected, so they can flow to each other and to stream regions. I won't go into detail here, but this is at one HRU or one landscape position. We're modeling many processes. We're driven, of course, by climate and by land use. We have full plant growth modeling in this model, so temperature and nitrogen cycling. So we can look at water and nitrogen movement in soils, in runoff. Interflow is in the variably or unsaturated part of the soils. And in many watersheds, we're also looking at groundwater. In this example I'm showing you, we don't have groundwater flow. So one of the questions was, when you delineate a watershed, how should you delineate it? How coarse, how fine? And so we had the opportunity to test that in 3 cases. First, we always use topography, because even if you have units delineated by land use, the flow can go to many locations. So each of these can flow to the channel and to another HRU. Then we used the soils map, which I showed you previously, and you can see how that kind of dissects some hill slopes. We get more spatial variability. And then finally, we had one where we actually have an HRU for each probe for comparison with the data. So we did that, we compared with data. I won't show you all that, but I just wanted to give you a feeling for the dynamics. So each of these maps are showing the soil water content from fairly dry to fairly wet at different times, from dry, intermediate, and wet. And here we're just showing those on a time series where we actually had, this is our wet period, this is one of the drier periods, and a lot of the period is actually not very wet either. And so these two look kind of similar. You can see the darker color means it's a little bit wetter. And we see the strong effects of crop management and land use, because the plant takes up moisture, and that shows up in the model as well as in our data. Obviously, when it is wetter, then we see some different patterns of wetting, especially down in the lower area. So these are simulated results of soil moisture, but they're calibrated to the measurements. We also calibrate something called saturated hydraulic conductivity. And in this case, you can see that depending on your delineation from coarser to finer, we have more detailed patterns. The important thing of this is to show you that when you're coarse, you don't really see this run off down the hill slope. And when you get finer, we start to see run-on effects. That is, the runoff accumulates as we go down slope, and that has an effect on the dynamics of both soil moisture and runoff. So this is really a research model use to answer some of these kinds of questions. Another little interesting study we did was, I showed you this topographic map of the field before in 2001. We did that again in 2009, and you can see the difference, right? Well, it's topography. We normally assume that it doesn't change, but when you take the difference of 2009 minus 2001, you can get the amount of, well, the elevation change, which we relate to either erosion or deposition. And this is the resulting map of change. So red is erosion and green is deposition. And if you remember the topography, there's a high area here. So the wind comes from the west, it scours here, so the red here, and it deposits here. This was not entirely my intuition. I thought that these hill slopes may erode more, but in fact, they're net depositional over this 8-year period. Other features we see are water erosion. So we have wind erosion. We can see features of water erosion in the channel and down slopes. And then of course, management. So because of the cover, we have a strong management effect, even some legacy of previous management. And this was a recent tillage event that they, for some reason, went very deep in these swaths. So this is just an example of using high precision detailed GPS to determine patterns of erosion deposition. So to conclude, the recent technological developments provide automated long-term measurements of spatial and temporal variables. Emphasis here is that we have a field site that we're maintaining for decades, and so these are a legacy of important data. The computer models are essential for process understanding and estimation over space and time. And key problems, I didn't go into all of these, but we have agricultural water management, which Dr. Zhang will talk about, land use change, and projected climate change. And as Dr. Fares mentioned, we do work internationally. So with that, I'll go to questions. I have many people to acknowledge. I won't name them all, but these are people who have worked directly with us. And I just thank you for your interest.
Thank you, Dr. Green, for this wonderful and excellent presentation. I would like to, I think, open the floor for a few questions, like so that we can, before we go to the next speaker. And we have here our dean, who may be leaving for another meeting, so we'd like to give him the opportunity to pitch in if he has something to say.
Well, thanks, Dr. Fares, and greetings to our guests. Much appreciate you taking the time to educate and illuminate us about the finer points of precision agriculture. And really excited about the opportunity to have this series organized by Dr. Fares. So yes, I do have to log off here in a little bit and join another Zoom call, but thanks so much and stay safe and well, everybody.
Well, thank you. Appreciate you coming. I'm sorry that Dr. Zhang didn't go first, so you could see some of her.
Well, we will have the link, so the people who don't have the opportunity can see this again. So we have, it's recorded.
Yeah.
I didn't say that disclaimer in the beginning. So, so any question, any comments from the rest of the audience? If you don't, I have a quick question for you, Tim. Please, you mentioned about those rain gauges. I think we had a discussion about it a couple of weeks ago about those Cadillacs versus your regular cars, to take an analogy there. So how is the comparison between those two rain gauges as far as accuracy?
Yes, thanks for asking. In fact, they compare very well. The Texas Electronics was the one I showed that has a large orifice. So it has a 9-inch approximately orifice. And even under some windy conditions, it does pretty well. A scientist who was actually my professor at University of Washington has done some studies of rain gauges, and he argues that you should bury your rain gauges. They should be at ground level because of wind effect. But he and I have had friendly arguments that that's not very practical on a farm where you have blowing material. So we have compared, and many of our gauges are actually only about 16 inches above the ground. And we actually have almost 20 of these gauges. There's some different types to look at spatial variability, but we have pretty good confidence in these measurements. We do acknowledge, though, that there's always a wind effect that we can't really predict, and there tends to be some underestimation because of wind, up to 10%.
And another question, since it seems nobody else is asking a question here, I would like to ask you a question about opportunity for our students and the graduate students for some internship, some summer internship with your program. Do you have any?
Right. Yeah, thanks for asking. I think that's something we want to explore. At this time, I don't know of any immediate openings if people are looking immediately, but we typically do, and Huiwei will talk about the field experiment we call LIRF, Limited Irrigation Research Farm. They have several students who are either students who are employed seasonally, or we also have a pathways program. I got some industry money recently, and we'll be hiring a PhD student to work with our model and extend that to doing some pesticide work. So when we get money, we definitely reach out and hire people, and that's part of our collaboration with Colorado State University. And I think, Ali, we can explore maybe shorter term things with some of your students. So I guess that's a vague answer in terms of, I don't know that we have immediate openings, but over time, yes, we definitely like to hire students and recent graduates.
Great. I mean, I know you will deliver. I mean, when you can. So I don't have any doubt about that. So I think your answer is fine. I think it's a good segue for us to introduce our second speakers, and we will have another opportunity to at the end for additional questions. So I would like to introduce our next speaker, Dr. Huiwei Zhang. Dr. Zhang received her PhD degree in biological and agricultural engineering not far away from here, from Texas A&M College Station. So she's an Aggie. Welcome back to Texas, at least virtually. So she also has an MS degree in electrical engineering from San Francisco State University in California, and a bachelor's in electrical engineering from China too. So she is currently a research physical scientist with the ARS, and also an associate faculty member in the Department of Civil Environmental Engineering at Colorado State University. Her research program focuses on developing methods for agricultural water management, limited irrigation management, estimation of crop water status, and crop water use using ground and UAV/airborne and satellite-based remote sensing technologies. Dr. Zhang, she's an associate editor for irrigation science and MDPI agronomy journals. She was the chair of the ET measurements and modeling community and biophysical measurement and sensors community under the climatology and modeling section of the Agronomy Society, of the American Society of Agronomy in 2019. I think with that, I would like to welcome Dr. Zhang. Welcome, Dr. Zhang.
Let me share my screen first. Thank you, Dr. Ferris, for the invite and the nice introduction. Let me see. Okay. You're able to hear me?
Yes, that's good.
Oh. Mm-hmm. Yeah.
Yes, you're right. Just put it on. Yep.
Okay, this will look good. As the second part of this talk, I will focusing on talking about how we use remote sensing technology for the research we conducted here in Colorado. Just a little bit background on irrigated agriculture in US. Irrigated agriculture, I think, will now make a big contribution to the value of the agricultural production. So, however, with as you can see, this figure with increasing limited and more costly water supplies, from 2007 to 2012, irrigated acre declined by nearly 0.8 million acre across the U.S. Most of the area decline occurred in western states where drought condition continued to water supply scarcity across the region. So much of the expansion in irrigated acres has occurred in more humid eastern states where we're used to be rain-fed agriculture. So to help maintain the farm productivity, profitability, efficient irrigation systems, and then water management practice are critical and needed. So to better manage irrigation, we need to answer the questions like when to irrigate and how much need to be irrigated. According to this 2018 Irrigation and Water Management Survey by the USDA National Agriculture Statistics Service, there are mainly 8 ways that's how farmers make irrigation decision now. So among total of there are 431,000 farms in the survey, about 63% of them still using the condition of crop and then feel of their soil method. So about among only 10% of them use a soil moisture sensing device or check the daily ET report. So most of them is still go with the traditional method. To quantify crop evapotranspiration is critical in research in irrigation management.
Wait, you hit your mute, I think.
Unmute it, please. Okay. So.
Okay. All right. Okay. Yeah. So ET is highly correlated to crop yield. Our unit has conducted limited irrigation research on corn in semi-arid, northern Colorado, and then find out this relationship between harvested corn yield and annual ET used by the local cropping system from planting to the grain maturity. So this figure shows the relationship between ET and the yield, which is also called the crop production function. So the 12 points on in each figure represents 12 treatments, which were under different level of irrigation at crop late growing vegetative stage and the maturation stage. So those colored dots indicate the treatment have a percentage of irrigation less than 4 at those growth period. Those the blue arrows highlights the treatment with water saving, which about 17%, but still maintained a full yield. So this treatment means 65-80 indicates we give water at 65% of ET during the late vegetative stage and 80% at maturation stage. So by saving those water, we still can maintain those yield. So this gives us the information on how ET is important to estimate and can help us to strategically manage irrigation to use our water. So recently, the advanced in-sensor technology has given us the opportunities and the capability of doing scientific irrigation scheduling, such as direct mirroring ET by weighing lasimeter or a energy balance-based covariance system. We can measuring soil or plant water status to determine how much water the field will need, or utilizing the weather data and the crop coefficient using the manual from FAO 56, or remotely sense the crop coefficient from a satellite or ground-based sensor to estimate the crop coefficient. So the bottom figure shows remote sensing like a NDVI will highly correlated to crop canopy cover and the crop coefficient. So next, I would like to talk about how sensor can help monitoring crop water stress. So when plants suffer stress, plants use less water than the maximum amount possible for well-watered conditions. So visually, you see stressed plants shows shorter plant head, less plant canopy, and then maybe curved leaf when stress is high. Here I give you the overview of our limited irrigation research farm, and where irrigation research was conducted on different crops like corn, sunflower at plot scale, and also like a field scale. So we're collecting data such as photosynthesis, gas exchange, leaf water potential, stamina conductance at leaf level to evaluate crop response to water stress. Those are point measurement and labor intensive. We also measure sap flow sensor, but rapid the sensor up bottom of the plant. You can track the water from the root to plant to determine crop transpiration. Or there is another one called mini reservoir imaging system to give you, monitoring the root growth and the root biomass. And from the deeper root zone to see how plant responds to water stress. And a neutron probe device or TDR sensor are used to measure soil water content at different soil depths to determine soil water deficit. So water deficit calculated by field capacity minus soil water content, which you can determine how you manage your, when soil water deficit below the readily available water, then the plant, we manage this crop as a deficit irrigation, but maintain this, all the soil water deficit above this line, then we maintain this plot as a fully watered irrigation plot. When crops suffer water stress, stomata tends to be closed to prevent plants from losing water. So crop transpiration will be reduced and the leaf canopy temperature will increase. So canopy temperature is a proof the indicator of plant stress. So, and then those parameters derived from canopy temperature, such as the crop water stress index, standard deviation of canopy temperature, has been used to quantify crop water stress level. So we collected the canopy temperature using infrared sensor, like a setup on top of the canopy, or a camera working with a smartphone, or handheld device, or research grade level thermal camera. We took a canopy temperature with those sensors. We developed an indicator like a canopy temperature, standard deviation of canopy temperature. All those values are well correlated with the plant level parameter, like leaf water potential, stamina conductance. And then also this indicator shows well response to water stress treatment along 2 growing seasons. So all this gives us the confidence to use remotely sensed information to monitor crop growth status and then help to make an irrigation decision. So unmanned area vehicle, or we usually call drone, or drone-based sensor and camera become more affordable these days. So UAV remote sensing not only provide high resolution imagery, flexible flight schedule, but also map a spatial variability within a field in a rapid way. For example, there is a 6-band multispectral camera would provide RGB or false color infrared image for us to measure canopy cover. As I mentioned before, canopy cover is highly correlated to crop coefficient. Then we are able to determine real-time crop coefficient from UAV images to make a prediction of the daily ET. And then another example with a thermal camera, we can map the surface temperature of canopy to determine crop water stress status as you can see from this thermal image corresponding to the RGB, so more stressed plants show more drier soil, so higher surface temperature. This three image on the left side from the top to the bottom will be the soil EC map, reflectance during UAV reflectance image, and then yield map, from the yield monitor. So this map covers an area with limited irrigation, and then this part with fully irrigated irrigation. So we can see in this area, more intense red color indicates healthier plants, and then so maybe more biomass. In this area treated with depth irrigation, we see more variation and then brighter reflectance colors due to the less plant growth and the dry soil background. We also observed this UAV images and the yield map of depth irrigation well corresponded to this soil EC map. So the darker color indicates more water holding capacity. And so yield in well-watered area is not affected by soil EC as in the area with deficit irrigation. And this map is the daily evapotranspiration we calculated from UAV multispectral and then thermal image. Also, you can see more variability in ET rate from this area than fully irrigated area. And from this high resolution UAV image, we can see where in the field the crop need more water. So the algorithm we used to calculate the ET from UAV data has the potential to be used in variable rate irrigation to produce irrigation prescription map. In this study, so UAV thermal imagery has a low resolution, about 8 centimeter compared to RGB imagery at 1.25 centimeter. So the surface temperature pixel from here, some pixel will be a mixed temperature of both soil and the canopy. So how can we utilize this thermal imagery? So in this study, we extract the canopy cover from this high resolution RGB images using a machine learning method. And then once we have accurate canopy cover, then we downscale this image to the resolution same as the thermal imagery. Then by multiply these two images using the image fusion method, then we extract the canopy temperature from this relatively low resolution of thermal image. So in this study, we involved sort of a machine learning method for image classification and then image fusion technique. Another study, we analyzed the 12 multispectral indexes calculated from this 5 bands of the UAV image, and then try to predict plant stomatal conductance status. So we compared the traditional linear regression and the machine learning algorithm for the prediction. And then finally, we use the best performed machine learning algorithm to determine stomatal conductance map for the 6th day during this growing season. And then based on that, a irrigation prescription map can be generated from those of the stomatal conductance image. So UAV remote sensing has some great potentials in agriculture production and research. So such as we can use the UAV data for yield prediction, irrigation scheduling, or detecting disease, weed, monitoring crop development like biomass, leaf area index, plant height, and monitoring response to fertilizer, indirectly estimate the soil water, or even help using the thermal image, helping us to detect the drip line leaks. For example, here we have subsurface drip irrigation. So once they have a drip line leak, instead of digging off the soil, then we're using a thermal to detect the leaking. But UAV remote sensing, the system has some limitations too, such as before you fly, you need to get FAA approval to fly the area. And then the battery life is pretty short for UAV system. You need multiple flights to cover a larger area. And you may get a poor quality of image due to changing weather conditions during the flight, and depends on the GPS accuracy. The overlap between each flight path varies a lot. And then right now, few commercial image processing software package can provide a fully automatic workflow. So, but with the AI and the machine learning technology, I believe these limitations can be overcome in the future. So overall, we are working towards irrigation automation with advanced sensing technology and then machine learning or AI. So multi-source and multi-scale data and the knowledge need to be integrated in this process. Last, I would like to acknowledge my colleague and the students who have been working together on this project for the past years. Oh, that's all I can share today. Thank you for your time. What?
Dr. Ferris, you're muted. You're muted, Dr. Ferris.
I lost.
Thank you. Thank you. I'm testing your ability to read ellipses. Well, thank you, Dr. Zhang, for this good presentation. And I think I open the floor right now for more questions and for questions for Dr. Zhang. So the floor is yours. Please proceed. I mean, she talked about very important topics about how to optimize water resources. I think we always think that the maximum amount of water produces the optimum return, but I think Dr. Zhang showed us that no, you can use optimum with less water, right?
Yes.
So I think it's, is there any, are you working closely with any animal research scientists in there, in the unit? So I think.
In the unit, oh, no, we don't do anything about animal.
Okay.
Maybe other unit in the center team.
Okay.
Rangeland, someone may working on cattle.
Yes, yeah, we do have the Central Plains.
Like a animal, movement. Yeah.
Mm-hmm. Yeah, there's a large property, Central Plains Experimental Range, where they do grazing studies and kind of long-term ecology work also.
Well, I think a question would be about was the response, I mean, have you tried the response in multiple crops and see basically the response for that reduced evapotranspiration or irrigation level at there? Was it like specific to specific crops, or it's the results are can be extrapolated to other crops?
Good question. Yeah, we conducted on several different crops, like a wheat, sunflower, bean. I think there's something else, but mainly reported now will be corn. We're still working on those methods for other crops. So hopefully can have the publication out soon. Yeah.
Okay.
Yeah. I think with the sensor, like a UAV method I presented here, definitely can be transferred to monitoring the stress. Those methods can be transferred to other crops, but maybe when you calculate the crop water stress, can be crop specific or location specific.
I think another additional question would be, how do you see the this type of applications can be used on the go? Because the ultimate goal for many farmers is really to have autonomous vehicles to minimize the labor. How do you see this type of information can be used to make a decision on the go and decide about, for example, irrigation or fertigation or crop pesticide treatment, etc.? How do you see this in the future?
So let me repeat your question. You mean how this technology can help farmers?
And I mean, in the decision on the go. I mean, basically, I think basically, how do you, while they are in the field, they don't have to go back and analyze the data and develop application maps, etc. How can we, while we are in the field, process it, take the data, analyze the data, and the robot who's handling the field will make the decision about where to apply and how long, and make the decision right there.
Yeah, that's it's my question too. I always ask myself how this can be used easily by the farmers. And then during our meeting recently in the group, we find out that farmers sometimes, especially for irrigation decision, they make a quick decision. They don't have much flexibility to long time to determine, how much I need to irrigate. Once they got water, they just turn on and irrigate. So I think the technology, although without this technology, there's still a long way to go for farmers can fully use this. Need different expertise to work together. Maybe we try to use less input from farmer from their field, but can help them to make a real-time decision. Then I think combine satellite, remote sensing or UAV, but not from farmers, but maybe from, there is a certain way you can get the data from their field, helping them, upload the data to the cloud service or some platform, help them to make a decision, but only get data input from them at the beginning of the season, not ask them to go back weekly or some bi-weekly to collecting data. So it needs to be. I feel like there is a long way to go for farmer to adopt those technologies. So that's why we talk about how this can help in research at this moment. Yeah.
Tim, you want to add to it?
Only one thing. This is not really my area, but I know the group in Bushland, Texas, near Amarillo, has been doing a lot of work with sensors mounted on irrigation pivots, and they already have the ability to do precision irrigation management and even fertigation. I think that precision ag has been around for 30 years or so. And it's always promised more than it's delivered. But I'm more hopeful that, like Weiwei is talking about, we have some of the things coming together to actually get to decision support in real time. Otherwise, most of the imagery and yield monitoring are more looking forward longer periods of time. But there is research in the area. I don't know how close we are to that being widely applied.
Thank you. I see Gary Newton. He wants to talk, I think.
I have a question. As long as Ali brought up livestock, presumably water resources are going to continue to be more and more scarce as population increases and the water resources are devoted to crops. What do you view as the future of the livestock industry in the United States? I'd like to get the opinions from the civil water engineers here on your views of how livestock may fit into this whole equation of water resource management.
Go ahead, Tim. Out of my area.
Thanks, Gary. I have a theory that if two people each have 50% accuracy in their knowledge, you don't get to add that, you multiply. So this probably may be more ignorance than knowledge. This is not exactly answering your question, but there is some good work related to soil health in particular, but moving grazing systems integrated with cropping systems, and there are mutual benefits. So I think that, you know, to compartmentalize land into either animal or food production in terms of grains is probably not our future. More integrated ag is probably the way to go. But again, I think that's work in progress.
Thank you.
What's
I think,
your
Gary,
knowledge of this
I
subject, Gary?
I think this is, you brought a good point. And I was going to take an analogy between what Huawei mentioned about like the optimum level of a crop production would be with less than 20% maximum ET. So I think there is an analogy there for the feed conversion for the animal. I mean, is this, maybe there is an optimum level of feeding the animal so that it will give an optimum level rather than to give them maximum feed or something similar to that. What's your intake on this?
Me?
Yeah.
Well, I think, you know, goats are our thing. Goats can get by on land that's not suitable for crop production. So I've always been an advocate of tailoring your land to your actual, to its abilities, tailoring your agriculture to the land. So if you have land that is suited for grazing, you graze that land, you don't try to grow crops on it. And I think that we have to perhaps break with our mold of saying, well, eat more beef, and say maybe we can't eat more beef because beef may take a lot more resources.
There you go.
Go with animals that are more efficient and help build the land, tailor our diets, change our behavior. So animals can still have have value there. We just may not be, we'll be paying more for it. And that's from an animal scientist. So.
Well, anything else? Our economist, Dr. Alfred Parks, you want to say something before we close? I mean, I think we need to, it has to be economically viable, right? Because we can talk about all the technology we want. I mean, at the bottom line, these farmers need to make a living, right?
Well, that's the whole goal. When we think about precision agriculture, of course, you know, we're always crunching the numbers to see, okay, is it economically viable? Of course, you know, those parameters change over time. You know, we always say what maybe was not feasible before, maybe feasible now. So that goes and comes based on the other parameters involved. But we understand that we're trying to make it sustainable. We want to use every tool in the toolkit. And of course, you know, us economists, we look at the bottom line and say, okay, it doesn't make economic sense. And I think in this instance that, you know, we're moving in the right direction. With improving the technology, and economics will catch up with us later sometimes.
Thank you. You don't have any comment about what Tim cartoons in the beginning?
Now I'm embarrassed about my cartoon because you have a nice economist. That wasn't even net return. That was just
Right.
Well, I would like to really thank you, Tim and Huawei. We really appreciate these insightful and great presentation that you have. We're definitely looking forward to further our collaboration. I think this is a beginning, and we would like to really collaborate, find opportunity, especially for our students, and definitely for our some of our research interest here, because as you know, the topic of what you're talking about is very relevant to what we have facing here in Texas. Water resources are limited, and we would like to optimize them. So I think what you are doing is great. We would like to really look for opportunity to collaborate. I think we would like to collaborate further more than just the water and your discipline. I think if there is opportunity for animal collaboration, for other opportunity, we welcome that too. So I would like to thank you, and I would like to appreciate it. I'd like to let you have the last talk, the last say here in this meeting, Tim.
Oh, well, thank you all for attending. I know we've run a little late, but yeah, I think there will be opportunities. One thing I would like to mention is we're currently developing both the ARS National Action Plan for our national program, which is a 5-year plan, and then our project plans are 5 years and then reviewed every 5 years. And we're developing that. And part of the process is to get I guess, input from stakeholders, collaborators. So this is actually a very good time for us to get your input. If you want to say, hey, maybe you should think about this. So those are good comments, and maybe we need a little follow-up meeting just on ways that we could collaborate in fact, instead of just too broadly. Yeah.
Thank you again. Thank you everybody for staying a little over the time, and I appreciate this great discussion, and you have a great rest of the week. Thank you all.
Thank you for your time. Thank you.